Hi, this is Peter Weiss, and this is my op-amp circuit. So this is the inverting op-amp. We have R2 and R1. This is 5.1 kilo ohm and 1 kilo ohm. We have the input here with this purple wire, and we're scoping the input and the output. And with 5.1 and 1, this should be a gain of about 5. The resistors aren't perfect, so it's not quite that. And this is our second op-amp. This is the follower op-amp, so the input would go in right here, and then the output is connected to the other input, and because of that, the gain should be about 1. And here is the differential op-amp. Right now it's in the common mode gain configuration, but we have R1 and R3 about 1 kilo ohm, and R2 and R4 about 5.1 kilo ohm, so the gain V2 minus V1 should be about 5 here too, but when we're in the common mode gain configuration, the gain's going to be much lower. It should be basically 0 because V1 is equal to V2. So looking here at the waveforms, this is for the inverting amplifier. You can see it's inverted, and this is 1 kilohertz with the square wave, and so you can't really see the slew rate, but if you switch to 10 kilohertz, you can see the slope very prominently, and you can calculate the slew rate. So we calculated the slew rate using the cursors here, and we see it's the delta y over delta x, which is the slope, is about negative 282 volts per millisecond, so it's about 0.28 volts per microsecond. It's not quite the 0.4 that was expected, but that's what we got, 0.28 volts per microsecond using these cursors. And now to measure the gain here, we use sine waves because that's what we have to do to measure the gain, and we see that the input is about 2.4 volts while the output is about 500 millivolts. So if we divide those, we get 4.8, which is about 5, the gain that we were expecting. And we can verify this with the frequency response. So we get 13 decibels at the starting frequency, which is about 5 not decibels. And now this is for the differential op-amp, so this is measuring the common mode gain. So we do that this amplitude over this amplitude, and we can calculate that using these values here that we use the cursors for. And if we calculate that, we get about 0.0068, which is a lot higher than what the expected one would be with the 90 decibel CMRNR value. It should be about like 0.0001, but because the resistors aren't perfect and R1 is not exactly equal to R3, R2 is not exactly equal to R4, we get a lot higher value because it's very sensitive to changes in that. So this is our common mode gain, 0.0068, and we can confirm that sort of using the frequency response. Here we'd start at negative 40. If we started a little less high of a frequency, like 100 hertz, we would see negative 43 decibels, which is about what 0.0068 is in not decibels. But we start a little higher, we get a gain of around negative 40, which is close enough to the gain that we calculated using the square waves of 0.0068. Okay, so that is